Hello everyone, welcome back to Logic Binder. In this video, we shall discuss about finite automata in brief. Finite automata is the fundamental concept in formal languages and automata theory. It is an abstract mathematical model of computation which is used to recognize patterns and process strings in a systematic way. The word finite means that it contains only a limited number of states. A finite automata reads an input string one symbol at a time. Based on the current state and input symbol, it moves from one state to another according to predefined transition rules. This process continues until all input symbols have been read. After processing the entire string, the machine checks its final states. If it ends in an accepting or final state, the input string is accepted. Otherwise, the input string is rejected. Coming to formal definition of finite automata, it is a phi tuple m equal to q sigma delta q naught f, where q represents a finite and non-empty set of states. Sigma represents a finite and non-empty set of input symbols, which is also called as input alphabet. Coming to delta, it is the transition function that defines how the automaton moves from one state to another based on the input symbol. Means here it is going to consider one state and on one input it is going to another state. Coming to Q naught, it is the initial state which is one of the states. And coming to capital F, it is set of final states. Means there could be more than one final state. Finite automata has many practical applications such as lexical analysis in compilers, text processing, pattern matching, network protocol designing, and also digital circuit design. Let us see the summary of finite automata. It is nothing but simple yet powerful computational model that processes input strings through a finite number of states and determines whether the input is accepted or rejected based on its final state. Types of automata, there are basically two types, without output and with output. In without output, there are DFA, NFA without epsilon, NFA with epsilon. Coming to with output, there are two types, Mealy and Moore machines. Now let us see a sample example for deterministic finite automata. Here, let us consider Q naught as initial state, some middle state and final state Q2. In DFA, suppose the sigma equal to 0 and 1. Input alphabet is 0 and 1. For Q naught, there must be transition for on 0 and also on 1. And on 0, there must be only one transition, and on 1 also there must be only one transition. Coming to Q1 also, there must be only one transition on 0. There must be only one transition on 1. Again, coming to Q2 also, there must be one transition on 0 and also one transition on 1. Means for any state combination and one input combination, there must be only one outgoing state. SLC, NFA, again sigma equal to 0, 1. See here in this diagram, Q naught is having two transition on input 0. It is going to Q1 and also Q2. Means on single input, a transition may go for multiple states. These kind of diagrams are called as NFA. Coming to NFA with epsilon, same as NFA, but you may have epsilon transitions like this. Means on without reading any input itself, it is going from Q0 to Q1, and it may go from 0 to 1 like this. Multiple transitions, it may have multiple transitions, 0. It's your wish. Again, see the difference between DFA and NFA. The main difference is if you consider a combination of a state and an input symbol, there will be only exactly one transition in DFA. Coming to NFA, there can be 0 or more transitions. That's why the transition function for DFA is Q cross sigma to Q. Means if you consider a state and a combination of one input, it will go only to one state. Coming to NFA, if you consider a state and a one input symbol, it may go to multiple states.